Hey everyone, welcome to assignment 61 relating f prime to f double prime and f. I want to look at a lot of things visually today, but I also want to do some reviews. So yeah, there's a lot of stuff here. All right, warm up it says. Complete the table. We've got these different points. We have f prime, and f double prime. So I'm wondering at x equals a, what we see. Well, f is above the x-axis, so I've got a positive there. F prime. Well, I see the function is decreasing at x equals a, so that's a negative. And what about f double prime? Well, I'm concave up until I get to this place, maybe this place. And so I'm going to say positive. Okay? So why don't you pause the video and see if you can fill out the rest of the form. Okay, see you in a bit. Hey, welcome back. So for B, I'm on the x-axis. F prime, well, I think the slope at that minimum is 0. And f double prime, well, all this is concave up, so I'm going with plus. What about C? C is over here. I definitely see concave down over here. I see concave up over here. I think that's an inflection point, so I'm going with a 0. The function is increasing here. F is increasing, so I'm going with plus. Oops, sorry. Going with plus for f prime. And then what about f? Well, I am going to have f positive for everything until g. So I'm just going to pre-fill those. Okay. And we said that at b, we have a 0, and we had a positive. D. So I'm looking over here. Function looks concave down there, so I'm going with a minus. And it looks like I might have a 0 slope there. E. This is concave down, and this appears concave up, so I think 0 there. Decreasing, 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 decreasing. The rest of those are minuses. And I think I'm concave down between f and g. But at this point, I seem to be concave up to concave down. So I'm going to say 0. And at g, I'm concave down. All right. So now we want to take this information and try and draw a graph of f prime. So what do we know about f prime here? Okay, well, f prime represents the slopes of this f graph at all these different points. All right, so I think putting in the 0 slopes is the best way to start. I'm going to put a 0 here and a 0 here. Now, I think there's a 0 here at f on f prime. Yeah, that looks like a 0 slope to me, so I'm going to have that be 0. Okay, now what do we see? Very negative slopes, less negative slopes, almost 0 but still a little negative slopes, and I get to 0. Now, positive slopes, very positive, that's about as positive as they get, and they get less and less positive as they head back to 0. Something like that. Now, these are all negative slopes. Here, bouncing, and something like that. So let's see if that worked. Okay, I have a negative slope, so I have a negative slope. Here, I still have a negative slope, but it's less negative. So I'm heading back to a 0 slope here, and then more and more negative slopes. Yes, I like that. Now, can I sketch a graph of f double prime? Okay, so what do we know about f double prime? Well, f double prime has a 0 here, and has a 0 here, and a 0 here. And so remember, f double prime is represented by the slopes on this f prime graph. Well, I see positive slopes, positive slopes, positive slopes on this graph until I get to, I think it's here is where I'm supposed to be. There we go. Yeah, because that was the steepest slope, so that's why this is the highest, so that's 0. Okay, these are all positive slopes. Very very positive, a little less positive, almost 0, 0. Okay. And now I see a bunch of negative slopes on f prime, so I'm going to be plotting negative values here. It looks like my most negative occurs at D, and then my slopes there we go, at E. So I think I'm going to go like that. And then between E and F, I have positive slopes. And then here I have negative slopes. So that's what my F double prime will look like. And one thing I wanted to point out was, so this is like that saddle point on x to the third. X to the third. So think about that, and then I take a derivative, and now I've got an x squared bounce. And I take a derivative, and now I'm passing through. Okay? But I would always start by plotting the 0 points first. And remember, we don't care about the y values here to tell us about the y values here. It's the slopes on this graph tell us what the y values are here. The slope numbers here, like a slope of 0, become y values on this f prime graph. Okay? So how about you try this one? Here's an f prime graph, and this is -2, 2, and 4. This is at 3. This is at 0. Okay, so we've got this f prime graph, and I'd like you to try graphing f double prime, and then we're going to do f. But first, f double prime. So we pause the video and draw me f double prime. Hi, welcome back, everyone. So I'm looking to draw f double prime, and I know that I like to start with the 0 slopes on f. That's a 0 slope. That's a 0 slope. Here I have very positive slopes. I know they're negative y values. I don't care about the y values. I'm only talking about the slopes. Very positive slope. A little less positive. Still positive, but even less. Almost 0, but still positive. And then I get my 0 slope. So very positive, less positive, until I get to 0. Here to here, I see only negative slopes. I see positive y values. I see negative y values. I don't care about those y values. I'm looking at the slopes. A little negative, more negative. That's about as negative as I get. Less negative, almost 0, 0 slopes. And so my graph would go something like that, where that most negative slope curve, where that most negative slope here became this point here. And then over here, I see lots of positive slopes, a little positive, more positive, very positive. And so my graph looks like that. And so I'm not really surprised that this third-degree polynomial with a positive leading coefficient has a derivative that's a second-degree polynomial with a positive leading coefficient. Okay, so with that in mind, how do we go and sketch an f graph from this? Well, when I'm graphing an f, I want to think about these y values were actually slopes on f. And so here, this y value of 0 on f prime is a 0 slope on f. And do I have a max or a min? Well, let's see. We've got this critical point, we've got this critical point, we've got this critical point on f prime. And I see f prime is negative over here. F prime is positive. prime is negative, f prime is positive. Well, when f prime goes from negative to positive, we know we have a min on f. And when f prime goes from positive to negative, we know we have a max on f. And when f prime goes from negative to positive, we have a min on f. So I need a minimum at -2, a maximum at +2, and a minimum at 4. Okay? And my function is decreasing until I get to that minimum. And then my function is increasing until I get to that maximum. And then my function is decreasing to that minimum at 4. And then increasing again. Both ends up. Makes sense to me because remember f prime was a positive third degree polynomial. So the antiderivative of f prime would be a fourth degree polynomial with a positive leading coefficient. Now, see how I've drawn this red graph so that it's bouncing here at 4 and above the x-axis and below the x-axis? Yet without more information, that's all completely arbitrary. I could shift this red graph down, I could shift this red graph up. Wouldn't matter where I put the red graph, I just need to be lined up with these zero slopes. These zero slopes put the zeros on my f prime graph. On my f prime graph, I see a 0 at -2, so I need a 0 slope on f. I see a 0 at 2, so I need a 0 slope at 2. I see a 0 here on the blue f prime graph, and so I need a 0 slope on f there. Okay, what's next? Well, how about this one? How about I tell you that we've got f prime information and f double prime information. And there's 1.916. And to the left of that point, f prime is positive and f double prime is positive. To the right of that point, f prime is positive, f double prime is negative. Can you sketch me a possible graph of f? Hi, welcome back. Okay, so what do I know? Well, I know 0.916 on one side, and on the left of that, I see increasing and concave up. And on the right of that, I see increasing and concave down. And at this point, I want to join these two pieces. So here's my x value of 0.916. I want to be concave up until I get there, and then concave down after I leave. But everywhere, f prime is positive, so everywhere my function is increasing. Okay, that's about all I have to say about that one. How about this one? What if I, instead of taking that information and putting it into a table, I gave you this? And here's a graph of f double prime. This is pi. This is f double prime. And let's call this 2 pi out here. And we've got this for f prime. That's going to be pi also. Okay. So I'd like you to sketch a possible f graph from this information. Give it a try. Think about this. It's okay to think. Think about this and come back if you have a graph or you've thought about it for a while and you still can't do it. All right, well, let's see what's going on here. F prime, f double prime. We've got pi, we've got 2 pi. It looks like f double prime is negative from 0 to pi, and f double prime has positive y values from pi to 2 pi. Okay. It looks like f prime is negative everywhere, here and Okay, so what do I see? Well, I don't see a sign change on f prime. And that means there's no min or max that I'm going to be thinking about on f. I just see decreasing zero slope decreasing. Is it? Is it? No, not zero. Still negative. I better put the pi there. So all of this is just negative. Great. Okay. And so f prime is negative means f is decreasing. F double prime, though, is first negative, then 0, then positive. So I guess I want to think about this as f is decreasing, but over here, f is decreasing in concave down, because f double prime is negative. And then here, we're still on a decreasing f, but now we're concave up. F is decreasing, but concave up. So I want I want decreasing and concave down, and then I want decreasing and concave up. This point is pi. This is 2 pi, and that is 0. All right, any questions about that possible f graph? So let's see. It looks like I might have a 0 slope here, which is why f prime has got a 0 value there. It looks like I might also have a 0 slope here, which is why f prime is back at 0 here. And these are all negative slopes, and that's the most negative slope, which is why I have this minimum on f prime at pi. Okay, yeah, I like that. All right, next. Let's put some stuff together because we've had a lot of information recently. If f prime is greater than 0, then what do I know? I know that f is increasing. Okay? And if f prime is less than 0, yeah, f is decreasing. Good. What about, though, what happens if f prime is increasing? Well, if f prime is increasing, that means f prime has positive slopes, which means f double prime is greater than 0, right? Because the slopes on this graph become the y values on this graph. Because f prime is increasing, that means f prime has positive slopes, which means that f double prime has to be greater than 0. But wait a minute. If f prime, a double prime, is greater than 0, didn't that also mean f was concave up? Yes, it did. And so if f prime is decreasing, then we know that f double prime is less than 0 because these are negative slopes, which means I have negative y values on f double prime. And that means that f is concave down. Okay. I will say many students really struggle with this set. You might want to put some asterisk around it as a reminder. Okay, so how do I find mins and maxes? What do I say there? Mins and maxes can occur at f prime equal to 0, but where else? That's right, f prime undefined. And finally, endpoints. Endpoints of a bounded interval. Good. Okay. How do I know, just because f prime is undefined or f prime is equal to 0, whether I have a min or a max? Well, remember, if your f prime sign chart goes positive to negative, then you have a max at x equals a. Do you need the justification sentence for that? Sure. f has a max at x equals a because to the left of x equals a, f prime is greater than 0, and to the right of x equals a, f prime is less than 0. Remember, for the rest of the year, anytime you have a max or a min, you write me that justification sentence. I want that to be a habit. Okay, what if we have this sign chart? What's that mean? That means that f has a min at x equals b. Why? Because to the left of x equals b, f prime is less than 0, and to the right of x equals b, f prime is greater than 0. Okay? All right, what about inflection points? Well, inflection points come when we have a change in concavity from concave up to concave down, or concave down to concave up. Okay, now I know my function is concave down when f double prime is less than 0, and then I have f double prime greater than 0 for concave up. So when I have this situation, I'm going to say this is an inflection point because I have a change in concavity on f. There's an inflection point at x equals c because f double prime changes sign at x equals c. So f double prime is negative, f double prime is positive, and that's equal to 0 with a sign change. So actually, I kind of want to take this a step further because we just talked about defending this inflection based on f double prime changing sign, either from negative to positive or from positive to negative. But what if we thought about this in terms of f prime? What must be happening on f prime so that on f double prime I have a 0 there? Well, f prime, since f double prime represents the slopes on f prime, I must have a 0 slope on f prime at this place. And because these y values are negative on f double prime, that must mean the slopes are negative on f prime. So negative slopes, a 0 slope, and then positive slopes. That's a minimum. Oh. So where f prime goes from decreasing to increasing. Hey, f prime, when f prime, the antiderivative of f double prime, when f prime goes from decreasing to increasing, that's going to be a 0 slope, which means I'm going to have a 0 y value here on f double prime. I have negative slopes here, so I have negative y values here. I have positive slopes here, so I have positive y values here. What I'm seeing is that when f prime goes from decreasing to increasing, or it turns out increasing to decreasing, if we have these situations, if f prime is doing this, then f has an inflection point. Yeah. You know, and just to think, they were doing all this in the 1600s. Uh, just want to say, that's pretty cool thinking, if you ask me. All right. Um, so if f prime is increasing, then f double prime is greater than 0. So f is concave up. And if f prime is decreasing, then f double prime will be less than 0, and so f will be concave down. Frequently, the AP exam puts us in this position. All right. Remember um, our justifications for endpoint maxes and mins, or be sure to be able to interpret what this means. Okay, so what do we know is going on at each of these points on F? So left endpoint, then F prime is positive. F must be going up from that point. So this is a min. Okay, I've got my endpoint, and then F is decreasing. So if F is decreasing, this must be a max. Okay. Kind of like writing it. So it's a min, it's a max. How about on the other endpoint? With our right endpoint where F is decreasing, F prime is negative, means F is decreasing until we get to this point. So that must be our min. And here I'm increasing on F until I get to this point, and so I call that a max. Being sure that you can write the justifications for these endpoint maxes and mins, that will be important as well. Now, I understand that the second derivative is often used to find inflection points, but also concave up, concave down on F. All right, but I want to talk about the other second derivative test, not this one that says, okay, F is concave up on negative infinity to A, and F is concave down on A to infinity. Yeah, that's second derivative test, all about concavity. But I want to use that other application of the second derivative. We can use the second derivative to help us find maxes and mins. No, really. I know, why would you want to? Because you've already found the first derivative. There are actually situations where we really want to use the second derivative because, yeah, I'm just not going to be able to do it the other way. So let's think about this shape. Here we have a minimum. And what can we say is happening both on F and F prime at this point? Well, F prime of A equals 0. Slope there is 0. And what about F double prime at A? What kind of concavity do you see? I see concave up, right? So F double prime must be positive. Okay. So here's what I want you to do. I want you to say, hey, if F prime is equal to 0 and F double prime is positive, then F has a min at x equals A. This is the second derivative test. The first second derivative test was this one. But we have this other second derivative test where the sign, SIGN, of the second derivative combined with the fact that f prime is 0 at that point, the sign of the second derivative informs me as to whether or not I have a max or a min. So what about this case? I know f prime of b, the slope at b is 0. But what about f prime? I'm sorry, f double prime at that same point? Yeah, it's concave down, so that means f double prime is negative. Now let's go backwards. If I know that f prime is 0 and at that same point f double prime is negative, then I know that f has a max. F has a max at b because f prime of b is 0 and f double prime of b is negative. In fact, that would be my justification. If I had to write the justification for this, I would say, and this is f, and I'm saying f has a min at x equals a because f prime of a equals 0 and f double prime of a is greater than 0. Now this feels like a lot less writing than our normal justification for a max or a min, which seems like maybe we should do this instead, except that this requires me to find f double prime first. And sometimes finding f double prime is just going to be so much work. It's just going to be so much easier just to write our first derivative test justification, which is when we see that sign change on f prime and write a sentence about it. Okay. Second derivative test. It's real. It's not going away. We usually use the second derivative test when we have x's and y's in our relationship. I'm trying to think of one offhand, and I think I shouldn't try. I should just go give us this other practice. Yes, ooh, and we need to do 1 and 2 with the calculator. So, how about this one? Y equals 5 minus x to the 1/3. And I want everything. I want max, I want min, I want inflection points, I want increasing and decreasing, I want concave up and concave down. Oh, and inflection points. Oh, we said that already. Okay, so go find all the stuff. Come back in a few minutes when you're done. Well, hi. So I'm just curious, did you think about this from a pre-cal point of view? It's the cube root of x graph flipped upside down and shifted up 5. We know that normally this is the cube root graph, but I want to shift this thing up 5, and I want to reflect it. So looking at that and that. And this point here is 0, 5. Okay. Now let's think about what we found here. Oh, look. This is decreasing, 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 decreasing. So everywhere this function is decreasing, this function is increasing never, right? Always going downhill, always going downhill, always going downhill. You can't say that this function is increasing if we're always going downhill. I'm bringing this up because on the next test, many people will in fact say that this graph is decreasing on some interval and then increasing on some other interval. And I don't know what they're thinking about even after all these years, but that's not the case here. All right, so let's see what we can find now calculusly. Y prime is going to be negative 1/3 x to the minus 2/3, or negative 1/3 x to the 2/3. Well, my denominator is equal to 0 if I put an x equals 0 in there, and that's going to be y prime undefined. Y prime undefined happens at x equals 0. To the left of x equals 0, let's put a negative number in. Negative 1 squared is 1. Cube root of 1 is going to be 1. 1 times 3 is 3. Negative 1 divided by 3 is negative. So I'm decreasing from negative infinity to 0. What about over here? What if I plug in a positive 1? 1 squared is 1. Cube root of 1 is 1. 1 times 3 is 3. I get the same thing. So this function is decreasing. This function is decreasing. But at 0, if I plug a 0 in there, I have negative 1 over 0, and that's undefined. So I'm undefined here. An undefined slope is a vertical slope on y at 0. Okay, so I see y is decreasing, y is decreasing. I don't have a sign change there, so there's no min or max. There's no endpoints to worry about, so I can keep going. What about y double prime? Okay, so if I take the derivative of this, y double prime would be 2/9 x to the minus 5/3, or 2 over 9 x to the 5/3. Well, again, if this is y double prime, 0, I'm undefined. Okay? And what about something in positive length? Well, I'm going to have 2 over 9, and that's going to be positive. But over here, if I plug in a negative 1, cube root of negative 1 is negative 1. Negative 1 to the 5th is negative 1 times negative 1 times negative 1 times negative 1 times negative 1. It's going to be negative 1. So I get negative 2/9 over here. So what do I see? I see a sign change that's happening at x equals 0 on y double prime. What does that sign change mean? Well, I know y is concave down, and then y is concave up. And so because y double prime changes sign at 0, I know I have an inflection point on y at 0. Now let's think about what we graphed, right? We graphed that Earth. That was our graph of negative cube root of x plus 5. Well, does it match what we discovered analytically with our calculus? Here's the point x equals 0. Am I decreasing and concave down to the left of x equals 0? Yes. Am I decreasing and concave up to the right of x equals 0? Yes. Because I have a sign change on y double prime, I have an inflection point at x equals 0. Yes, from concave down to concave up. Okay? All right, and remember, you need to write justifications. We have no sign change in y prime, but inflection point has a sign change. So I, of course, will write the justification and say, there is an inflection point on y at x equals 0 because y double prime changes sign at x equals 0. Okay, great. Now, I'd like to do a problem on our calculator. Please. Y equals 4x to the 4th minus 7x squared plus 4x plus 6. And conveniently, this doesn't factor by grouping. So what are we supposed to do? Well, I'm not worried about factoring this. I'm thinking calculously about derivatives. I'm thinking about that. And I want to be thinking about that. So can we find the stuff that we need to find? I'm looking for maxes and mins. I'm looking for increasing and decreasing. Yeah, it would feel better if I can't factor that, I don't think. The factors of 64 that add up to negative. That's not ringing a bell to me. Oh, but wait. Wasn't this supposed to be with calculator? Yes, please, don't fall for this. It's gonna blow away so much of your time. It's the calculator portion. Use the magic box. I know you want to know how to do stuff, but I'm just saying, it's the calculator portion. 7x to the second. is 4x plus 6. 4x to the fourth, 7x squared, 4x plus 6. Okay, now I actually don't want that function on. I mean, I can have it on. I can do zoom standard, and I can say, oh, look, here's a fourth degree polynomial. I only see two x-intercepts. I'm guessing the other x-intercepts are imaginary. It looks like somewhere over here in negative land, I'm going to have a zero slope. But really, again, not so interested about that, because I want to talk about using n-deriv math. N-deriv of y1, comma, x, comma, x. If you have a new school calculator, you're going to be given d, and then there's going to be a box, and then there's going to be a thing, and then there's going to be a this, and it's going to say x equals, and then another box. So when we want to graph a derivative, you have to put an x here. This is either you type in the function, or if you type the function into y1, then you put y1 here. And since we want the graph and not the derivative at a point, we plug an x here. And that's what we see here. y1 in terms of x at this x value, all x values. Okay? So now I'm going to graph the derivative. Okay, I see 1, 2, 3 x-intercepts. I could believe a third degree polynomial would have 3 x-intercepts. Okay. So what am I looking for? Remember, I'm looking for maxes and mins, so I can find that maximum. I do want to change my viewing window. -3 to +3. Just wanted to spread things out a little bit. Okay, so these places on y prime, these places are going to be places where y has a zero slope. These three places on y prime are where the maxes and mins are for this function. So second, calculate 0. Prime, and I get negative 0.055. Oops, there's a 1 there. Okay, there's my first critical point, and I see y prime is negative, and then y prime is positive. So negative, positive. Second, calculate 0. And I'm scooching down here. Somewhere. And hit enter. Go to the other side. Hit enter. And I get this place over here. 0.7296, so 730. I see positive y values and the negative y values. Okay. And my third 0 occurs at point. Did you find the same one? I think I found the same one because I'm getting 0.730. I wonder if that one's right. Alright, well, let's just try again. The third one. Okay. To the right. So this one must be wrong. Second, calculate 0. Enter. 0.325. Yes, 0.325. Okay, so now I have these values. And I can say y is decreasing on negative infinity to negative 1.055 union 0.325, comma 0.730. And I can say y is increasing on negative 1.055, comma 0.325, union 0.730 to infinity. I can see that there's a min here on y, because to the left of this number, y prime is less than 0, and to the right of this number, y prime is greater than 0. I see I have a maximum here on y, because to the left of this point, y prime is greater than 0, and to the right of this point, y prime is less than 0. So I have a max there, and then I have a min here at 0.73, because to the left of 0.73, y prime is less than 0, and to the right of 0.73, y prime is greater than 0. So I can talk about maxes and mins. I can talk about increasing and decreasing. What about concavity? Well, if I actually go back to this function for a second, let's turn this one off. Turn the first one on. So 6. I'm supposed to have a minimum. I see a minimum. But then I'm supposed to have a maximum. There's a maximum. There's a little jiggle in there. Look at that. Okay. So I could do second calculate minimum to find that minimum instead of using the first derivative. But when it comes to finding inflection points, I don't have anything over here that helps me find inflection points called, hey, calculate inflection point. So I think I need to appeal to y double prime. I guess I could always think about when y prime goes from increasing to decreasing, or when y prime goes from decreasing to increasing. Those would be places where y double prime, the slopes of y prime, would equal 0. But, I didn't do that. So instead, what I'm going to do is I'm going to come back to y equals here. I'm going to have that turned off. I'm going to have that one turned off, but now I'm going to go to this one and do n deriv again. This time I want n deriv of y2, comma x, comma y2, comma x, comma x. Okay. So now when I hit graph, I'm getting a graph of the second derivative. And I'm looking for intercepts on y double prime where I have a sign change. I don't feel like I see anything here. What's going on? Well, let's think about this for a moment. We said that y prime is 16x to the third minus 14x plus 4. And we said y double prime was 48x squared minus 14. Oh, look, it showed up. This is a very narrow parabola. There we go. And so I want to find my zeros. My zeros here happen at 14 over 48. I guess I can turn that into 7 over 24. And take the square root. Don't forget the plus or minus. See, there's the minus one, there's the plus one. So, and do I see that sign change on y double prime? Negative root 7 over 24, positive root 7 over 24. I see y double prime is positive, then negative, then positive again. Right? It's parabola. Okay, so we've got that, and now what do we know? We know y is concave up from negative infinity up to this point, union from this point to infinity, because y double prime is greater than 0. We know that y is concave down from this point to this point because y double prime is less than 0. And we see the sign changes here and the sign changes here. And so we know that these two are inflection points, and we need to write the justifications for those as well. You will be called on to determine values with your calculator. You are expected to be comfortable with that. So if you're not, reach out, let me know. We'll talk about it, okay? All right, I think we should do one last question. I think that one should be y equals x square root 9 minus x squared. Okay, will you go find all the stuff and come back when you're done? Okay, welcome back. So if I'm looking for maxes and mins, increasing and decreasing, I need the derivative of this, which is going to be x times 1/2 9 minus x squared to the negative 1/2 times negative 2x plus 9 minus x squared to the 1/2 times 1. So I'm going to factor this out. I think I'm going to cancel that with that. I'm going to factor out the smallest power, 9 minus x squared to the negative 1/2. What's left over? Well, this is gone. This canceled over here. I have negative x times x. Now this plus sign. I factored a negative 1/2 out here. So I'm going to have 9 minus x squared here. Okay, combine that terms. So there's my y prime. If I set this equal to 0, I'm finding when y prime is equal to 0. If I set this equal to 0, I'm finding when y prime is undefined. So y prime is undefined, negative 3 and 3. And here, 9 halves, square root of 9 halves. Square root of 9 halves, negative square root of 9 halves. Okay, so let's test some points in y prime. I'll plug a 0 in. 0, 0. I have a 9 on top, and I have square root of 9 on the bottom. 9 divided by 3, positive 3. Okay, so this is square root of 4.5. 4.5. Well, it's bigger than 4. So it's bigger than the square root of 4, which would be 2. So I don't want to test 2. If I test 3, I'm going to run into a problem here. Or, yeah. So instead, I'd like something in between these. Can I think of something in between? Yeah, I'm not really sure. Square root of 5. Don't get it. Square root of 5. Why square root of 5? Because this is square root of 5 squared, which is 5. 5 times 2 is 10. 9 minus 10 is negative. If I put in my square root of 5 here, I've got square root of 5 squared, which is 5. 9 minus 5 is 4. And now I've got this 1 over square root of 4, and that's positive. So I have negative divided by positive, and that gives me a negative 4. If I repeat the same process over here with negative root 5, squaring turns all those negatives into positives, so I'm good there as well. So what do we have on y at these points? Well, at this point, because y double prime goes from negative to positive, I see a min on y. And at this point, when I see y prime going from positive to negative, I know at this x value on y, I'm going to have a maximum. But wait, there's more. What's happening here at x equals negative 3? From this point, y is decreasing. Y is decreasing, so this must be a max. Max, min, max. What about here? The function is decreasing until we get to 3. 3 is the low point, so that's a min. How did I know that these were endpoints? Well, I got that from here. Um, this is that semicircle. If I try and plug in a 4, 9 minus 16 is negative. So you can, test out here, but you shouldn't get anything on these ends because we have a restricted domain situation. We know that y is decreasing and decreasing. We know that y is increasing between these 2 points. Okay? And then how did the second derivative go? Let's take a look at that. Y double prime equals negative 1/2 9 minus x squared to the negative 3/2 times negative 2x times this guy plus this guy times the derivative of this. Okay, well, we've got some factoring we can do. We can take that out. We can cancel a 2. Negative times negative is a positive. So I'm going to have x times this stuff. So I'm going to have x minus 2x to the third. And then I factored out negative 3/2 here. So that's going to leave me with 9 minus x squared times this minus 4x. If I distribute this minus 4x, I have minus 36x, and that was minus a minus is plus 4x to the third. Okay, combine like terms. I feel like so that's going to be 2x to the third minus 27x. Okay, and you can factor that, right? You can take out an x and that 2x squared minus 27. And don't forget that GCF that we pulled out, right? It was 9 minus x squared to the minus 3/2. So here's our y double prime. And it looks like y double prime is undefined here. At negative exponent says this is on the bottom, and the bottom equals 0 at plus or minus 3. X equals 0. And then here, this is going to be 27 over 2. Now, here's the thing about 27 over 2. 27 over 2 is 13.5. Well, that's square root of 27 over 2. Square root of 27 over 2. Let's think about square root of 27 over 2. That's the square root of 13.5. Well, the square root of 16 is 4. And the square root of 9 is 3. So this is between 3 or 4. But wait a minute. Didn't we just get through saying that we had a bounded interval from negative 3 to 3? So these points, they're beyond that. So they're not going to work. So the only y double prime I've got to consider is that one, I guess. So what do we know? Well, we know 0, negative 3, 3, y double prime. Because over here, we have square root of 27 over 2. And over here, negative square root of 27 over 2. So here's my y double prime. If I plug a 1 in, this is going to be negative. That's going to be 1, positive. And that's going to be positive. Positive times negative, I get negative. If I plug in a negative 1 over here, this is still positive. But positive. No, this is positive, but that's still negative. And now this is negative. Negative times positive is positive. And I can say I've got an inflection point at y because at x equals 0, y double prime changes sign. And I can say that y is concave up from negative 3 to 0, and y is concave down from 0 to 3. And I can write the justification for both of those. So that's what you need to be able to do. You need to be able to do it by hand. You need to be able to do it on your calculator. See you in the next video, everyone.